Hey everyone, I want to continue our study of quotient groups, and we'll pick up with where we left off, I guess you could say. So more really just examples of how to get a handle on quotient groups and what the group tells you about the quotient. And this one, I'm going to call this a theorem. I don't know if it's really important enough that we want to call it a theorem, but that's how I have it labeled. So let's say that we have G, and it's going to be a direct product, let's say H cross K. And H, let's call it H bar, it's going to be the set of all ordered pairs of the form H comma, what do I want, H comma identity? H comma identity, where little h runs through all of capital H. So in a way, what you can think of is that this is a copy of capital H sitting inside H cross K. Right, sitting inside G. And it goes like this. So then H bar is a normal subgroup of G. And if you look at the quotient, G mod H bar, it's isomorphic to K. So, and that's definitely a bar there. So here's a way to think of this, I guess. This really is a copy of capital H sitting inside the direct product, right? And so when you take the quotient, you can imagine that what we're doing is just smashing H down into a point, into nothing, and so you're left with K, right? So this quotient right here smashes H away, and what you're left with is K. For the proof, let's see. So I want to apply the first isomorphism theorem. So what I want to do, let's think about what we're going to do. We would like to come up with a homomorphism from G to K that's onto with kernel H bar. And so there's really kind of an obvious choice here. So let's define phi from G to K by phi of, okay, so we need to input an ordered pair little h comma little k. The output needs to be an element of capital K. The obvious thing to do is to be K. Then, of course, this, I'll just say check. I'll say check. And the details are all easy to do, so I'm just going to say check. Phi is an epimorphism. All right, the homomorphism part's pretty obvious. It's onto because all you got to do anytime you choose a little k, there's a whole bunch of choices of h comma k that you can plug in to get that output. So it's onto. The kernel is going to be exactly the things that go to the identity over here. And so what would you need? You would need something that has e right here. So anything with the form h comma e is going to be in the kernel. So to check that phi is an epimorphism with the kernel of phi equal to exactly h bar. So then by first isomorphism theorem, G mod h bar isomorphic to K. So there's really just a sort of straightforward application. And one of the things that you want to start getting used to doing and thinking about is, all right, we would like to say something about a particular quotient. So you need to figure out, and the whole game is figuring out who is the correct, what's the correct formula for your homomorphism phi. Now, what we've seen so far is that if you know something about G, you can find something out about the quotient, right? So so far the theme has been you have some information about G, and then that will tell you something about the quotient. That was the content of the last theorem we had. I guess that was 15.1. In a sense, 15.2. It goes the other way, though. You can also use information about the quotient to get information about G. So that's the next thing we want to do. So sort of a new subject or a new theme here, using G mod n to get information info about G. And so this first example, kind of a, I don't know, famous example, I guess you could say. So remember what Lagrange's theorem said. So recall Lagrange, right? And it says if, for finite groups, so if H is a subgroup of G, then the order of H divides the order of G. Now, this next example is going to show that the converse is false. So, the next example shows that the converse, I guess you could call this the converse, is false in the following sense. We will show that just because you have a subgroup, just because you have a divisor of the order does not guarantee that you have a subgroup of that order. So let me say, I muffed that a little bit. If you have a number that divides the order of G, that does not guarantee a subgroup of G that has that order. Right? So divisors do not one-to-one correspond to subgroups. So the example is going to be this one. So example A4 has no subgroup of order 6. Now notice A4, let's see, what's the order of A4? Well, it's going to be 4 factorial over 2, so that means that A4 has order 12. 6 is clearly a divisor of A4, and so we're going to show that even though 6 divides the order of A4, there is no subgroup corresponding to that particular divisor. And the proof goes like this. It'll actually be by contradiction. So suppose that H, I'm going to call it H, yeah. So suppose H is a subgroup of A4 with the order of H equal to 6. So suppose we have a subgroup of order 4. Now, since the order of A4 is equal to 12, we have the index of H in A4 is equal to 2. And then by a previous homework, we know, so we can say, and so we know that anytime when we have index 2, right, the corresponding subgroup has to be normal. So we can say, and so H is a normal subgroup of A4. All right, well, that means that we can look at the quotient, and the quotient will have 2 elements in it, or we'll have size 2, order 2, which means it's got to be isomorphic to Z2. So it follows that A4 mod H is isomorphic to Z2. Now, what does that mean? Well, okay, so let's think now. How does Z2 behave? Well, it's only got 2 elements. It has an identity element and an element of order 2. Right? So order 1 or order 2, and that's all you got. So this implies, or let's say thus, for each, let's say alpha in A4, if I look at the coset, alpha times H, how do I want to say this? Yeah, it's either equal to H, meaning it's the identity coset already, or it has order 2, which would mean that alpha squared H equals H, right? So either order 1 or order 2. All right, either the identity or it's not. And if it's not the identity, then it's got to have order 2. Yeah, I mean, maybe just let me say it like this. So the reason here, any element of A4 mod H has order 1 or 2. Right, so what does that mean then? It means that alpha squared is going to be an element of H for every single alpha. So this implies, or let's say as a consequence, alpha squared is an element of H for every alpha in A4, right? It's either in H to begin with. If not, then its square has to be in H. If it's in, then of course the square of it's in there also. Now, let's just take a look at some of the elements of A4 now, right? So let's say this, note that 1, 2, 3 squared equals 1, 3, 2. So what this 1, 2, 3 is an even permutation, which means that it lives in A4. And so if I square it, this is what we get. This has to be an element of H. Who else? 1, 3, 2 squared. That equals, I think it's 1, 2, 3. Yeah, 1, 2, 3. So that one's an element of H. All right? Every time I take an element in A4 and square it, it has to live in H. So what we have now is we have these two elements in H. And I can kind of play the same game, so similarly. So what this means is now every time I take an element of A4 and square it, that element has to be in H. So similarly, and I'm just going to write down this list, 1, 2, 4, 1, 4, 2. Each of these are squares, right? 1, 2, 4 it squared is equal to 1, 4, 2. 1, 4, 2 squared is equal to 1, 2, 4. And I'm going to keep going down the list. 1, 3, 4, and it must be 1, 4, 3. Who else? 2, 3, 4, 2, 4, 3, 2, 3, 4, and 2, 4, 3. Also the identity, all of these have to be elements of H. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, which tells me that H has at least 9 elements. But remember what we said, order of H is equal to 6. So we can say thus, the order of H is at least 9, right? A contradiction. Right? Therefore, no such H could have existed, no such subgroup of order 6 could exist. Because if it had order 6, then it would have to have at least 9 elements, which obviously is impossible. Right? So there's a nice example of using the quotient, right? The quotient, the fact that it had order 2, and we had some information about, we know about groups of order 2, that allowed us to get some information about the nature of subgroups inside A4. It can't have a subgroup of order 6. And I just want to compare this. So let's say compare this with, it was corollary 11.6, which told us that if you have an abelian group, a finite abelian group, and a divisor of the order, then you're guaranteed to have a subgroup of that order, right? So corollary 11.6 said if G is finite abelian and N divides the order of G, then G has a subgroup of order n, right? So in the abelian situation, and right, that's the key, in the abelian setting, right, we're guaranteed for every divisor of the order, we have a subgroup of that order. So the reason that this worked out, this previous example right there, right, the reason we found that there was no subgroup of order 6, right, was because A4 is non-abelian. Where am I at? Okay. Well, let me just erase all this here. So let me just remind you. So let's say recall if G is any group, then the center of G is the normal. We show that the center is always normal, so it's the normal subgroup Z of G, right? And it's the set of all, let's say the set of all x in capital G, such that Gx equals xg for all little g in capital G, right? So it's the set of all elements to commute with everybody in G. One thing to notice, we'll say note, if G is abelian, then the center of G is everything, right? If you're abelian, then everybody commutes with everybody, so everybody's in the center. Now, this is kind of a famous theorem. I mean, this one appears every once in a while on the qualifying exam. So if you're going on to the master's program and you want to take was it Math 561, you've got to pass a qualifying exam. And so this theorem sometimes shows up on there. And so it goes like this. If what do I say? Oh yeah. If G mod ZG is cyclic, then G is abelian. So this continues our theme of getting information about G from knowledge about the quotient. So that something about the quotient, right, in this case being cyclic, forces us to conclude that G is abelian. So it tells us something about G. And of course, now, once you know that G is abelian, then the fact that it's cyclic, I don't know, kind of collapses everything, and you find out that ZG actually is all of G. Right. Okay, so for the proof, what we're going to do is assume that we've got a cyclic group here, which means that we've got a generator. And then we need to show that everybody inside G commutes. Let's go like this. So let's let little g in capital G be such that the subgroup generated by the coset GZG is equal to G mod ZG, right? So little g times Z of G is a generator for our quotient right there. Okay, so now we want to show that G is abelian. So let's take a couple of elements in G. So if little g and h are in capital G, I'd like to show that GH is equal to h times G. Oh, and I shouldn't have used, I got to use something else, huh? What did I use in my proof here? You know what? I used X. Can I change? Sorry. I'm going to change that little g and that little g. Call the generator X times ZG, right? So the coset representative of the generator is going to be little x. So now, if G and H are in G, then, well, what we know, so then there exist, let's see, let's call them M and N in Z, such that the coset G times Z of G is equal to X to the M Z of G, and the coset H times Z of G is equal to X to the N times Z of G. Okay, now what I want to do is I need to multiply G times H and compare that with H times G. And so let's think about what this is telling us now. G lives inside this coset right here, which is this coset, which means that G can be expressed as X to the M times somebody in the center. Same thing for H. So then there exist, let's say, little a and little b in Z of G, such that G equals X to the M times A, and H equals X to the N times B. Now, if I look at GH, that's going to equal X to the M times A times X to the N times B. And now we need to use the fact that A and B live in the center, so they can commute, they can slide wherever they want. And so this is equal to, let's see, where do I want it? Well, okay, so I'm going to just start interchanging things. I want it to say H times G in the N, so this is equal to, well, okay, so the X to the N can push all the way through, right? So this is equal, let me write out the details. Sorry, I'm getting X to the M times X to the N A B. So all I did was I interchanged the A and the X to the N. That's equal to X to the N, X to the M, AB. And now I want to push the B through, and I can do so because it is in the center. So that's X to the N. It'll interchange with A, and it'll interchange with X to the M. So it'll be X to the N, B times X to the N, A. And that's equal to H times G. Right? Therefore, our group is abelian. Right? So that's the end of the... Well, let me write a concluding sentence here. All right, but this is awesome. This is... I don't usually use the word awesome, but it just kind of came out automatically. This is really cool. Right? This is fun. Right? So what do we have here? Therefore, capital G is abelian. All right, so that completes the proof. This is one that you should study and pay attention to. Maybe I'll put it on the final even. So I think that's a good place to stop. Yeah, that's fine. Let me see what comes next. Yeah, this is fine. Oh, let me write this concluding thing. So just as a sort of commentary, so theorem 15.3 is typically used in its contrapositive form. So let's see. Our theorem said that if the quotient is cyclic, then the group is abelian. So the contrapositive would say if the group is not abelian, then the quotient is not cyclic. So it would be if G is not abelian, then G mod ZG is not cyclic. Yeah, now that's a good place to stop. So we will see you next time. Okay, bye.